So the third stress that I had mentioned at the beginning of the video was a change in volume of the system for gases in equilibrium. Okay. A change in volume for this system for gases will result in, if the volume decreases, if there's a decrease in the volume, then the equilibrium will drive toward the side with the smallest number of moles of gas. Okay, conversely, if you increase the volume, the equilibrium will drive toward the side with the largest number of moles of gas. Okay? Now, this actually shouldn't, number of moles of gas. So this actually shouldn't come too much of a surprise, because when we were talking about entropy, remember that entropy, when you increase the volume, the entropy will increase because it's driving towards more disorder. And if you have a higher number of moles of gas with a larger volume, this would equate to having a higher entropy, which is always what it's trying to achieve. Okay, the reverse of that is by decreasing the volume here, you're going to shift the equilibrium toward the smaller number of moles of gas. Okay, so let me give you an example. So let's take this example where we have nitrosyl chloride going to, or in equilibrium with, nitric oxide and chlorine gas. So if I increase the volume of this particular system, notice here that I have 2 moles of gas on the reactant side and 1, 2, 3 moles of gas on the product side. 3 moles of gas on the product side. So if I increase the volume, this overall equilibrium is going to shift toward the side that has a greater number of moles of gas. Okay? Conversely, if I were to decrease the volume, it would shift toward the side that has fewer number of moles of gas. Now let's look at an equilibrium that is heterogeneous. Now remember what heterogeneous means. It just contains more than one state here. So we have solids and we also have a gas. Okay, so if I increase the volume of this vessel, remember that the rule is that it's only going to shift to the number of moles of gas. So on the reactant side, I actually have 0 moles of gas, and on the product side, I have 1 mole of gas, right, per reaction. So if I increase the volume of this particular equilibrium system, the overall equilibrium is going to shift towards the products, right? And conversely, if I decrease the volume, it's going to shift towards the reactants. Okay, just because you're shifting to the side with fewer moles of gas. Now remember, the equilibrium constant here is only the concentration in regards to CO2, because solids aren't included within the equilibrium expression. So now let's move on to the last point that I wanted to talk about with Le Chatelier's principle. That is that the effect of temperature has on the equilibrium. Okay, so a temperature, I don't know if you guys have noticed, but every time I have written a K sub C, I've tried to specify what the particular temperature was at that given equilibrium constant, because the temperature depends on what the equilibrium constant, the equilibrium constant depends on the temperature of the system. Okay? So let's take the example N2O4 in equilibrium with NO2. As you see here, I have the enthalpy change for this system is 58.0 kilojoules per mole. That means that it's an endothermic reaction. Okay? Another way to say that is that energy has to go into this system in order to make this reaction occur. Okay? So if you increase the heat, it will change the direction in which the equilibrium will shift or decrease. It just depends. One easy way to determine this is it actually depends on whether or not it's an endothermic or exothermic reaction. Okay, so for this particular one, it's an endothermic reaction. So we're going to treat heat as a product. So we can rewrite this as heat plus N2O4 gas in equilibrium with 2NO2 gas. And then if we treat heat as a reactant, we can apply the same rules that we did with the first point, where you add or take away a reactant, it will shift the equilibrium accordingly, right? So if you were to increase the temperature of this system here, that means you would essentially be adding a reactant, okay? And remember, when you add a reactant, you shift towards the product side, okay? You will shift towards the product side. Conversely, if you were to decrease the temperature, that would be synonymous to say you would be taking away reactant, right? If you're taking away reactant, that means you shift the overall equilibrium towards the reactant side. Now, this isn't entirely a valid way to calculate things, because heat is never really a product or a reactant, right? It doesn't actually contain any sort of concentration, right, that you would put into an equilibrium expression. It's just an easy way to get us to think about how it would shift the overall equilibrium by adding heat or taking away heat, right? So if you have a change in temperature, though, that means that your K sub C will also change depending on what that temperature is, right? So any particular concentration of NO2 or N2O4 would be affected by the amount of heat that's in the overall equilibrium. Okay, so let's look at another example, and this one is an exothermic example, okay? It's an exothermic reaction. So I have heat here as a product because heat leaves the system, right? So that's why heat is treated as a product. When you have an equilibrium, say at room temperature, okay, at 25 degrees C, for instance, you have a nice mixture of this purple solution here. The reason being is because this cobalt chloride itself is blue, while the hydrated cobalt is pink. Okay, so if you have a combination of the two, right, you're going to end up getting this nice little purple equilibrium here. So if I apply a stress to this equilibrium by applying some heat, by raising the temperature, right, and just put a little Bunsen burner underneath this beaker, if I increase the heat of that system, because this is an exothermic process, the overall equilibrium is going to shift towards the reactants, okay? And that's exactly what you see in the test tube. You see in the test tube that you get more of the blue color, meaning that there's more of this cobalt chloride now present because you added heat to the system and drove the reaction towards the products. Now let's go in the opposite direction in terms of stressing the system. So if you decrease the amount of heat, see if you decrease the amount of heat, see these this ice within the bath here, you decrease the amount of heat, that means that you will drive the overall reaction, or excuse me, the equilibrium towards the product side, right? You're forming more of this hydrated cobalt compound, which is the pink here. So you're driving the overall equilibrium towards the reactants because you're decreasing the amount of heat in the system. So notice here that I'm going to have a different K sub C for all of these, right? So if for this, for the blue reaction, I'll have more reactant. Say if we're just keeping it generic here, I'll have a higher amount of reactant on the bottom, okay? And then of my equilibrium expression. So if I'm in equilibrium, though, if I'm at, say, room temperature here with the purple solution, I'm going to have closer to like a 1/1, for instance, okay? And then once I go over here where I have more product, right, then I'm going to have a larger number on top. So my overall equilibrium constant changes depending on how much heat has been added or taken away from the system, right? And they certainly are not equal to one another.